right, so let's count up the work, see what we get. So let's do the same kind of fill in the blanks. So think about an arbitrary level J. How many subproblems do we have at level J? A to the J. You start with 1, it proliferates, there's 8 times as many on the next level each time. Okay, so J levels down, you're going to have A to the J. So, size of each level J subproblem is going to be what? Say it again? I just didn't hear it. N over B to the J. Same kind of reasoning. Initially, the input size is n. You drop it by a b factor every time. So J levels down, you've dropped it by a b factor J times. So that's n over b to the J. Okay, so let's put it together. So again, the point is we're taking horizontal slices of the tree. We want to look at the work done in a given horizontal slice, a given level. So total work performed at level J, not counting work done by recursive calls. Okay, so just done by these level J recursive calls. Is, need some more real estate here. Well, we're going to do the same thing. We're just going to say, well, multiply the number of subproblems we have at this level times the work we do on each subproblem. Now, where can we look up the work that we do per subproblem? Where's that going to come from? Right, so clearly there's an A to the J term here. So again, remember what we're doing. We're taking the jth horizontal slice. We're saying how much work do we do at this level? Well, clearly we got to multiply by the number of nodes at this level, the number of subproblems. Now we need to multiply the work that we do for each of the subproblems. Thus far, we have figured out that the size of a subproblem at level J is n over b to the J. How much work do we do on a subproblem of size n over b to the J? So here we got to go back to the recurrence, right? So the input to the master method. The input for the master method says, look, you do some work in recursive calls, you make A of them, each one has is a b factor smaller, plus you do some stuff that's not in the recursive calls. And that's the big O of n to the d term. Okay? And I went ahead and wrote out the constant. So we have a c n to the d. So what we have to do is we have to apply this. The meaning of this is work performed, not counting what's in the recursive calls. So that's work performed on something that has size n. Now we're working on subproblems that have size n over b to the j. Okay, so what we do is we substitute n over b to the j in that for n. And what we get is c times n over b to the j raised to the d. Okay? Again, number of subproblems. Number of subproblems at level J, size of a subproblem at level J, work performed on one such subproblem. That's where all that comes from. Okay? All right, so let me group this so that I'm going to separate the stuff which is independent of J and then the stuff which does depend on J. So I'm going to bring out this C n to the D. None of that depends on J. Times A over B to the D raised to the J. Rearranging. And this now is the grand entrance, stage right, of the A versus B to the D tug of war, which governs which of the three cases that we're in. Remember, those are the two crucial quantities, A and B to the D, and for the first time we see them in the same room. All right. So before delving into the cases, there's not much we can say except for the following. So for the total work, all we can sort of do is add this up over all of the levels. Okay? So this stuff is independent of the level J. So we have a C n to the D times sum over the levels, which go from level 0 up to log base B of n. This thing. Okay? So we're going to call this star. This is sort of a natural, it doesn't look like it, doesn't look like much, except the alphabet soup, but this is a milestone, this is a sort of rest point in our analysis. Okay? So again, any handwriting questions? Any questions on how we got here? So what have we proved? We've proved that for, given as input any recurrence of this form, no matter what the parameters A, B, and D are, this recursion tree argument shows that the total work performed is no more than this ugly thing, star. Now we don't know what this is. We don't know how to interpret this or relate to it. I still have to do that for you. But I just want you to agree that this is correct. Whatever A, B, and D are, this is a legitimate upper bound on the total number of operations over all of the recursive calls that this algorithm performs. Are you agreeing up to that point? All right, so now from here on out, it's more interpretation, it's more fun. Okay, because we're going to say, what does this actually mean? But it's important that you agree that this is correct. Yeah.
What is the n over b to j over there?
That is the size of a problem at level j, because we're cutting by b each time. Okay? So, let me start telling you how you should think about this crazy expression star. And why it's actually expressing something very meaningful. Even to the non-mathematician, just to the programmer uninterested in math per se. This is actually expressing something very easy to relate to. Yeah?
Could you elaborate on how you came up with the information?
All I did was I took this. So remember, what we derived here was an upper bound on the total work in the jth slice at level j. So I just summed over all of the different slices. So remember, the levels start at 0, with level 0, level 1, all the way down to level log base b of n. And so that's just this, summed over j going from 0 to log base b of n.
Are we going to go on constant work from base case?
No. That will actually govern one of the cases. Good. Other questions? Yep.
Where does that come from? I know you said that equation.
Yeah, so good. So that's C. Every year I kind of debate whether to put it in there or be sloppy about it. And because I'm doing kind of so many detailed calculations, I decided to just be explicit about it. I thought otherwise it would be confusing. To answer your question, that C is the C hidden in the big O notation in the recurrence. So if you prefer, think of it that we're given a recurrence which is expressed as A t of n over b plus C n to the d. Okay, so the C belongs right there. Now the C just carries through this entire proof in the most innocuous way imaginable. So it has no conceptual content. It plays no role in what the final true answer is. That's why I think about omitting it. But I worry it's confusing to I worry it's confusing to have big O's flying around in the middle of this derivation. Okay, so C, it's something, but it's by far the least important letter on the board. Okay, but it's a fair question. So that's what it is. Because at the end, that C is just going to get sucked back into our big O's in the master method. Okay. All right. So conceptual. So how should you interpret this thing? Right. Well, really, I mentioned on Thursday this tug of wills, this tug of war between the forces of good and evil. Okay. The forces of good being that every time we recurse, it's on a smaller subproblem, so we The forces of evil being that there's this kind of scary proliferation of subproblems. Everything calls itself, often more than once, they call themselves, and so on. Okay, so that tug of war is distilled exactly in the ratio between these two terms.